In lesson 8.1, where we're identifying quadratic functions, we're going to start with some of the things in it today, but we're going to finish up with the others tomorrow. So a quadratic function is any function, an equation, that can be written in the standard form. And here's what standard form looks like for So of standard form, y equals ax squared, I forgot the a in front of the x squared, I'm sorry, let's go back to that. So y equals ax squared plus bx plus c. And we're already used to this for when we were factoring quadratics. When we had to factor quadratic trinomials, we identified the a, the b, and the c to help us out for factoring. So, but it says where a cannot equal something, what do you suppose it is that a can't be equal to? What do you suppose a can't be equal to? In other words, a is being multiplied by x squared. What do you suppose it is that a can't be, or we'd have a problem? It wouldn't be quadratic anymore. 0, yeah. If you multiply by 0, we will have no x squareds, because 0 times x squared, they'd be gone. It would no longer have the x squared term, so it would no longer be of degree 2, so therefore it would no longer be quadratic. So we need to have at least a has to be something other than 0. It can be anything else, but it just can't be 0. Did it say anything about, are there any restrictions on b or c? Did it say b can't be 0? No. Does it say c can't be 0? No, because notice if b is equal to 0, then we'd only have two terms. We'd have the ax squared and the c term, well then we just have a binomial instead of a trinomial. Or if c was equal to 0, then we'd only have two terms, and we'd still have a quadratic binomial. But if both b and c were equal to 0, then we'd still have the ax squared term, we'd still have one term left, and it would be a quadratic monomial. So we can have b and or c equal to 0, we just can't have a equal to 0. Okay, the basic quadratic function is called the parent function. Every family of functions has what's called a parent function, the most basic one. And it is y equals x squared. So if I say to you, graph the parent function, I'm asking you to graph y equals x squared. What's a equal on that? What's x squared being multiplied by? Invisibly. 1, yeah. So a is 1. Remember when we were factoring quadratic trinomials? And we said, what does a equal? If a is equal to 1, then we just get to use the diamond method. If a is equal to something other than 1, then we had to do the diamond method and factoring by grouping. Well, here a is equal to 1. What's our b equal to? Are there any x's? No, there's just some x squareds. There are no x's. So what would you have to multiply x by to make them go away? 0. So b is equal to 0. What do you suppose c is equal to? 0, because if you add 0 to something, it doesn't change it. So our c value is also 0. So remember what I said. b and c can be equal to 0, but a can't be. So in the parent function, b and c are equal to 0, and a is equal to 1. The most basic quadratic function there is. The graph of one is a smooth curve called starts with p, parabola. Parabola. So it's P-A-R-A. Unless you would say para, but it's para. And then we add the bola behind it. So parabola. And notice what its shape is. It's a U-shaped graph. So when you have a U-shaped graph, when you can very nicely connect through the points and make a nice U, you have yourself a parabola. Or in other words, if you graph a quadratic function, you better get a U-shaped graph or something went wrong.
So I'm guessing we're graphing again?
We will be graphing again. Not today yet, but we will be. Okay, so a parabola will either open up or it will open down. Opening up, The U is in its form that we're typically look at it. If it's opening down, we have an upside down U. Okay, so, and it's the A value that controls this. So whatever your A is, that says, okay, I'm going to help. One of my roles is to tell you whether it's going to open up or it's going to open down before you even graph it. When A is greater than 0, what kind of numbers are greater than 0? 1, 2, 3, 4, 5. What's their sign? They're positive. All numbers greater than 0 are positive. So when A is positive, it opens up. So when you have a positive A value, something greater than 0, you should end up with a U that's in its regular orientation. It should be opening up. When A is less than 0, what kind of numbers are less than 0? What kind of a number is negative? Or that's negative. So if A is negative, it opens down. And notice it doesn't say anything about when A is equal to 0. Why not? What about 0 itself? What about when A is equal to 0? It's not quadratic, right? Remember, it said up there A can't be equal to 0. So if A is equal to 0, then you're probably right, Jossie. It would probably just end up being a line instead of being a graph. Okay, well, notice something about U's. When you're even writing a U, what happens? You're moving along with your pencil, and you've got this nice, movement going. You start maybe at the top, and you're moving down, and then all of a sudden, what happens? It switches. You change direction, and you start going back up again, don't you? So when we have a parabola, a U-shaped graph, it changes direction. At a point, an ordered pair, some point on there, and it's called a vertex. So where that U-shaped graph makes its turn, we call that point the vertex. Okay, well, there's also some kind of important things that they like to ask us about the graph of a parabola and some information about it. It says, when the parabola opens up, so I have a little picture there for us in our notes of that, the y value of the vertex. What's the y value? It's the second value in the ordered pair, and it's the up or the down, isn't it? So the y value of that vertex actually becomes the lowest one on there. It would be the lowest y value of any point on this curve. This one right here, the vertex itself, that would be the smallest y value there is, and we call that a minimum. Which should make sense to you. If you have a job and you're getting paid minimum wage, they can't pay you any less than that, can they? That's the least you can make. That's the smallest amount. Okay. Well, when the parabola opens up, or opens down, I mean, when we have an upside down U, that y value of that vertex is now the highest one. It's the biggest y value of all the points on that parabola. So what are you supposed to call it now? Instead of a minimum, it's a maximum. So when they ask you for the minimum or the maximum of the function, they're really asking you for the y value of the vertex. They're saying to you, what's the y value of that vertex? If it's a parabola opening up, then it's got to be a minimum because it's going to be the lowest. Because that's where it makes its turn, and now it starts getting higher again. If it's opening down, that y value is going to be a maximum because it was climbing till it got to that, and then all of a sudden it stopped and changed, started going down again, so it becomes the highest point, the maximum. Okay, and then there's another characteristic of the quadratic function and the graph itself that we have to understand. It has an imaginary line. We don't typically draw it. You won't see it typically drawn in there, but it has an imaginary line that divides that parabola into two symmetric halves called an axis of symmetry. So there's some symmetry going on. What happened on one side of that vertex is going to happen on the other side of the vertex. Because it's like there's a reflection going on. So all of these are things that we're going to have to be able to pick out and understand in our quadratic functions. when we're identifying things about them, and when we're graphing them. Okay, let's go to the back side, and let's figure out how do we identify if a function is quadratic when it's given in equation form. So in other words, we don't have a graph to look at and say, oh, that's a u, that's quadratic. If we don't have a graph to look at, and we just want to do it, and I know how well you like to graph. If you want to be able to identify it just from the equation alone and not have to graph it, we got to have a method to do that. So what we're going to do is we're going to get the y alone. So if the y is not alone in the equation by itself on one side, like we did in linear equations, remember we used to get y by itself and put it into slope-intercept form. We can do the same thing in quadratic functions. We can get the y by itself. We don't talk about slope-intercept form anymore though. We write the other side in standard form. So we want it ax squared plus bx plus c form. And then we determine if it is of the y equals ax squared plus bx plus c form, that standard form. So we're going to look at it and say, oh, can I say that it fits this model? And if it does, we're going to say, oh, then it would be a quadratic U-shaped graph. Okay, so let's practice that. Number 1, y plus 6x equals negative 14. Y by itself? Okay, so our first move would be? Subtract 6x from both sides. We want to get the y by itself. So now we have y alone on the left side, and we have negative 14. Take away that 6x.
Add the opposite.
And then we'll change it to add the opposite. Now it said put it in standard form. So in other words, get the power on x, the one that has the highest power on x gets to be first, and then it goes down from there. So should the negative 14 and the negative 6x trade places or not? Does anybody remember what happens when you have just a constant, like negative 14? What power is x being taken to in that one? No. What's the only thing you can multiply by negative 14 by and it stays negative 14? 1. The only thing you can multiply negative 14 by and keep it negative 14 is multiplying it by 1. Tell me what power, tell me what power on x gives you 1. X to what power is 1? X to the 0 power. So negative 14 could be rewritten negative 14 x to the 0 power. So is it in standard form right now? No, those x to those two need to trade places because now we have x to the first power first and the x to the 0 power, which is invisible, second. What do you think? Is this standard form of a quadratic function? Is this ax squared plus bx plus c?
Yeah.
Well, if it is, what's a equal?
1, 0.
0. Oh.
I don't get this.
In other words, a equals 0,
And then it would just cancel out.
and b equals
Negative 14.
negative
Oh, 6.
6, and c equals
Negative 14.
negative 14. We're asking ourselves if this is quadratic or not. Is it quadratic? No. Why not?
Oh, it is.
Because a equals 0. You can't have a equal to 0. You have to have an x squared term. So we're going to say not quadratic. It's not quadratic. And the reason why is right here. Yeah. A equals 0, that one right there says, you know what, it can't be quadratic. A can't be equal to 0. Because then that would mean there are no x squares. And notice, we don't have any x squares, do we?
I don't get this.
Okay, so what kind of questions do you want to ask me?
Where do you get the 0 from?
Because there is nothing there, so you have to use 0. remember when there are no x squareds, that means a had to be equal to 0 because multiplying something by 0 would make them go away. So it's kind of like saying we have 0 x squares.
When we do the next one, I like it.
Okay.
Okay,
Okay, let's do number 2. Is y by itself? No, so we're going to subtract 2x squared, is that what I heard? Okay, so subtract 2x squared from both sides. Now we have y by itself, and we have 3x, subtract 1, subtract that 2x squared. In other words, we're just going to write it horizontally now. And then doing one of our favorite things, change it to add the opposite. And why is changing it to add the opposite useful here? Because what do we need to do next? Rearrange it. We need to put it in standard form. So standard form, what's that going to look like? Y equals.
Negative 2x squared plus 3x plus negative 1.
Okay. So you guys, what we're doing is we're taking polynomials and putting them in standard form. You did that back in chapter 7. That 3x plus negative 1 plus negative 2x squared is just a polynomial. And now we're just putting it in standard form. And now we're going to identify our a, b, and c. So what's our a this time?
Negative 2.
Negative 2. What's our b? 3. What's our c? Negative 1. Is this quadratic?
Yes.
Yeah, this is quadratic. And what's our reason? Right here. We have an a value that's not equal to 0.
So is that what we're doing today?
That's some of what you're doing today. Yes.
So.
Okay, so anybody got any other questions they want to ask about how can we tell from the equation without having to graph it? So would number 1 give us a U-shaped graph?
No.
No, because we found out it's not quadratic. Would number 2 give us a U-shaped graph if we had
Yes.
to graph it? Yes, it would. Anybody think they know right now what direction it would open?
Upside down.
It would open upside down. Why is it going to open upside down?
Because it's negative.
Because it has a negative a value.
Yeah.
Can anybody tell me right now then, would there be a minimum or would there be a maximum? Remember, it's the highest or lowest y
Oh,
value.
max.
It's a maximum. They would have a maximum, then we don't know what that is right now because we don't know what the vertex is. We can't tell you what it is. We can at least tell you it would have a maximum. Okay. Well then, the other thing you have to do is identify from a table of values. In other words, we have some ordered pairs, but we still don't want to have to graph it. We just want to take that table of ordered pairs and we want to follow something that will help us decide if it's quadratic without graphing it. So to identify if a table of values or a set of ordered pairs, that's really what's going on here. We have several sets of ordered pairs. Here they are, okay? It says, if you want to decide if it represents a quadratic function, look for a second common difference in y. So you need to look for a second common difference in y. Well, what does difference mean? What's going on when you talk about difference? Subtraction. So we got to find the change in y. Okay. So what we're going to do is we're going to go to our table, and we don't even have to. The only thing we have to worry about with the x's is, are they making a constant change? What's happening with the x's? They're going down by 1?
Or up since
They're actually going up by 1. So all of these are going up by 1. So as long as all of them are doing the same thing, and they are, so since all of these are going up by 1, then we can say, oh, x has a constant change of 1. So now I can check it out to see if it's quadratic or not. I can use all of the y values in that table. So the first thing we have to do is find the first difference. And then we'll find the second difference. So finding the first difference means this. What do you have to do to get from the first y value to the second y value? Subtract. Okay, what are we gonna take away?
39 subtract 18.
Okay.
Which one you want?
So does it go up by 21 or down by 21?
Down by 20.
It goes down by 21. 39 take away 18 is 21, but it went down 21, not up 21, so that's why we have to make it negative. Okay, how about 18 to 3 now?
Went down
15.
It goes down 15. 18 take away 3 is 15, but it went down, so it's a negative 15. How about from 3 to negative 6?
9.
So it went down 9, so we say negative 9.
And then down 3.
And then, this is kind of like you can think about the temperature right now. It's 6 below 0, it's going down to 9 degrees. What did it do? It went down 3, didn't it? Okay? That's our first difference in y. Is that a common difference? In other words, are all of them the same?
No, they
No.
are going to 3.
But they all are multiples of 3, yeah? But it's still not a common difference, is it? So then now what we're going to do is we're going to take it another step further, and we're going to say, okay, now I can find the common differences again, or the second difference, and see if it's common. Because if it is a second common difference, then we can say it's quadratic. So now we just do the same thing we just did again. What did we have to do to get from negative 21 to negative 15?
Subtract.
Okay, so what is negative 21 subtract negative 15?
6.
6. Okay, did it go up 6 or did it go down 6?
Down 6. I have it up 6.
Did it go up 6?
Yeah.
Okay,
Or
so
the
we're going to
negative
say
sign.
a positive 6, right? How about from negative 15 to negative 9?
6.
It goes up 6. How about from negative 9 to negative 3?
6.
It goes up 6. Do we have a common second difference? This is our second difference. Second difference in y. Write that on there. We just found the second difference in y. If all of them are the same, we can say it is quadratic. So because we have a common second difference, we're going to say this one is quadratic. If we graphed it, we would get a U-shaped graph. And the reason is because we have a common second difference. If you do a second difference and it is in common, then you can't say it's quadratic. If you do a first difference and it's already, if it's common in the first difference, you just stop right there and say, wait a minute, I already got my common difference in the first difference. It can't be quadratic because that can't show up until the second difference. If it shows up in the first difference, does anybody remember what kind of a function it is? What if that common difference shows up in the first difference? Anybody remember what kind of a function that is? What are the other types of functions we've studied?
Functions like
Linear function.
Oh, yeah.
Oh my goodness. Such retention we have. Okay.